This question requires you to express derived units into SI base units. Being able to express derived units into SI base units is important at AS physics level. So how is a named SI unit expressed into SI base unit? How do you recall the correct SI base unit of a derived physical quantity? In this lecture, I will also dwell into how a given physical quantity can have more than one SI unit, but only one SI base unit. Also, we shall discuss how a physical quantity can have more than one SI unit, but more than one unit. Now, being able to express named units or a combination of named units into SI units is important at AS physics level. Base units include the kilogram, the meter, the second, the ampere, the Kelvin, the mole, and the candela, although we usually don't deal with the seventh one. Named units, on the other hand, include such units such as Newton, Joule, Watt, Pascal, Coulomb, Farad, Weber, Tesla, and many others. These units are named in honor of scientists who have contributed to the development of various concepts in physics. For instance, the Newton is named after Sir Isaac Newton after his great works in mechanics. In fact, there is a branch of physics which is named after Sir Isaac Newton. This branch is mechanics. It is more commonly referred to as Newtonian mechanics. Now, each derived unit must be defined. It is defined because the derived physical quantity is also defined. It is common in physics, especially at AS physics level, to show how the named unit is expressed into SI base unit. For example, the Newton is a named unit. It can be expressed into SI base unit as kilograms meter per second squared. Now, how is this done? How is a named unit such as the Newton expressed into SI base unit such as kilograms meter per second squared? And then, how do you recall the correct SI base unit of a derived physical quantity? There are two steps required to convert a named unit into an SI base unit. Let's consider step number 1. In step 1, you will be required to recall the 7 basic physical quantities and the correct SI base unit for each one of them. The 7 basic physical quantities include mass, length, time, electric current, thermodynamic temperature, amount of substance, and luminous intensity. Although again, the 7th basic physical quantity, which is luminous intensity, we hardly deal with it at this level. So the first step is to remember them. To remember the names of the 7 basic physical quantities and the SI base unit of each one of them. Now, it is important to remember that there are only 7 basic physical quantities, and therefore, there are only 7 SI base units. Any other physical quantity mentioned in physics must be a derived physical quantity. The word derive means obtain from. It is referred to as a derived physical quantity because it is obtained from other physical quantities. These other physical quantities may themselves be basic physical quantities or derived physical quantities. In physics, when a physical quantity is derived, it is said to have been defined. To define a physical quantity in physics is to show how it is related to other physical quantities. These other physical quantities which are used in the definition must either be basic physical quantities or must have been earlier defined. This now takes you to step number 2. But it is important to note here that definition of physical quantities in physics must be learned. You must learn how a derived physical quantity is defined. This is one of the areas in physics where you have to recall something. This means that in an exam, you either know it or you don't know it. In order to recall these definitions, you must repeat them as often as possible. There is no other way around this. This means practicing a lot. Now let's look at step number 2. In step number 2, you must recall the equation which is associated with the definition of the derived physical quantity. As soon as the definition is given in words, it is immediately followed by an equation which shows you how the new physical quantity is related to the other physical quantities. There are few situations where a physical quantity is given, but there is no clear equation associated with the definition. In such a case, the definition is just a description of the term and not a definition in the most strict sense. An example is the definition of force. When you are introduced to force at a very basic level, you must have been told that a force is defined as either a push or a pull. To be very strict, the push or pull is not a definition of force, since there is no equation which is associated with this definition. The terms push or pull just describes what forces do. It is only later on when you encounter the concept of momentum that you are able to define the term force as change in momentum per unit time or rate of change of momentum. This is now the correct definition of force, since there is an equation associated with the definition. Another point to note here is that there is only one equation which is associated with the definition of that physical quantity. This equation must be learned and recalled as such. This is something which confuses very many students. This confusion occurs when a given physical quantity has more than one equation, which can be used to calculate it. I'm going to give an example here. Now we know that pressure is defined using this equation, force over area, especially in solids. Pressure at a point in a liquid can also be calculated by multiplying the density of the liquid with the depth of the point from the surface of the liquid and with the gravitational field strength. You can see that this physical quantity, which is pressure, can be calculated using two equations. But there is only one equation which is associated with the definition of pressure, and this is this equation here. Pressure is defined as force exerted normally per unit area. So the ratio of the force to the area gives us pressure. This equation here is obtained from this equation there. So in a situation where you are to choose which equation is the correct equation for definition of a physical quantity, you must be able to recall the correct one. So remember that there is only one equation which is associated with the definition of that physical quantity. This equation must be learned and recalled as such. This is something which confuses very many students. This confusion occurs when a given physical quantity has more than one equation which can be used to calculate it. Notice that I'm talking about the equation which is used to calculate that physical quantity. For instance, pressure is calculated using force and area, and at the same time in a liquid it can be calculated using the density, the depth, and the gravitational field strength. The examiner is particularly fond of examining the students in this area. To escape this trap, it is important that the definition of a physical quantity be learned correctly and the equation be recalled correctly the way it is learned. So you cannot escape from this. It is important to recall the definitions of the physical quantities used at AS physics level and the equations which are associated with that definition. However, a given physical quantity can have more than one unit. For instance, let's look at density. Density can be expressed in kilograms per meters cubed or grams per centimeters cubed. Notice that I'm talking about the unit of the physical quantity, not the SI unit. There is a difference. So density can be measured in kilograms per meters cubed or grams per centimeters cubed because these are units. However, the SI unit of density is only one, and this is kilograms per meters cubed, and not grams per centimeters cubed. You should therefore be able to recall the SI unit of physical quantities and distinguish it from any other unit which is used. In most cases, however, you should be able to convert from one unit into another one. For instance, at this point, you should be able to recall that 1000 kilograms per meters cubed is actually equal to 1 gram per centimeters cubed. This would be important where you have to convert from maybe kilograms per meters cubed into grams per centimeters cubed and vice versa. This one is referred to as a conversion unit. Just like you should be able to convert meters into centimeters and vice versa using this other conversion unit. This one is very important in physics. In fact, it is very, very common. The final point I'd like you to note about unit is that a given physical quantity may have more than one SI unit, but only one SI base unit. This mostly occurs where named units are used. Let's look at an example. The SI unit of pressure is newtons per meters squared. The SI unit of pressure can also be pascals. These are SI units of pressure. But the base units of pressure, the SI base unit is kilograms per meter per second squared. This is the SI base unit of pressure. So how is the SI base unit of a derived physical quantity obtained? This is the SI base unit of pressure. Pressure is a derived physical quantity. We are asking, how is the SI base unit of a derived physical quantity obtained? So in order to compare units or to know whether or not a given unit is the same as another unit, as it is in this question, it is important to express all units into SI base units. But how is this done? How do you convert other units into SI base unit? I'm going to use this example here to show how we obtain this as the SI base unit of pressure. From the definition of pressure, which is force over area, I realize that area is a derived physical quantity, force is a derived physical quantity, and force is defined from the equation mass times acceleration, because mass times acceleration is the rate of change of momentum, of course divided by area here. At this point, I can express each one of these into base units. Mass is expressed in, or it's measured in kilograms. Acceleration is measured in meters per second squared. And area is in meters squared. Now, at this point, don't confuse this m that I've used here with this m. This m stands for mass, while this m here stands for meters. So kilograms has got no other unit to cancel with, but this one and this one will give us meters raised to power 1 times meters raised to power minus 2. That gives us minus 1. And of course, seconds has got no other second to combine with, so it remains like that. That is why we say that the SI base unit of pressure is this value here, kilograms per meter per second squared. Although the same physical quantity can be measured in other SI units. Newton per meter squared is an SI unit of pressure. Pascal is an SI unit of pressure. But there is only one SI base unit. This one is very, very important for us to be able to understand. We are talking about SI base units. This physical quantity, pressure, has got two SI units, Newton per meter squared and Pascal. But when it comes to base units, SI base units, it has only one SI base unit. That is why it is important to be able to convert other units, especially named units, into SI base units, because it allows us to compare, as we are going to see in this question. So in order to compare units, or to know whether or not a given unit is the same as another unit, it is important to express all the units into SI base units. And how is this done? I've already given you an example. Now, I have provided a PDF document in the video description for you to download. In this PDF, I have listed all the physical quantities you need to recall at AS physics level. I have given their definitions, the equations which is associated with the definition, the SI unit, and the SI base unit. I have also given a few examples of how you convert other units, especially named units, into SI base units. I will encourage you to try and see how you can derive the SI base units instead of recalling them, because the process of recalling so many units can be a little bit tedious and it makes physics to be difficult. So I'm going to use this example to show you how you go about deriving SI base units of certain units, especially when the units are named units. So let's go straight to this example. This example comes from the 2017 October-November paper 1, variant 1, question 1. And let's see how it's done. Which pair of units are not the same when expressed in SI base unit? So we want to compare this unit and this unit. This unit is already in SI base units because you can see every unit here is an SI base unit. Meter is the SI base unit of length. Second is the SI base unit of time. But when we come to the right, the only SI base unit here is the kilogram. The Newton is not. So we need to convert the Newton into an SI base unit. The Newton is the SI unit of force. Force is defined as the rate of change of momentum. That is mass times acceleration. Again, the mass here has got nothing to do with this m here. This is meters, while this is mass. This is the equation which is associated with the definition of force. Again, don't lose sight of the fact that I'm showing you how to convert named units into SI base units. The first step here is to recall the equation associated with the definition. And here, because I'm looking at Newton, I need to recall the equation which is used to define force. So in order for me to get the SI base units of force, I need the SI base units of mass. Let me write it in full there so that I don't confuse it with anything else. But the A here, which is acceleration, can remain like that. The SI base unit of mass is, of course, kilogram. That of accelerations is meter per second squared. So as far as the Newton is concerned, that is how I would express it in SI base units. So when we come to Newton per kilogram, this will be given by kilogram meter per second squared multiplied by per kilogram. And you'll obviously see that this one cancels out with this, and I remain with meters per second squared. And you can see that Newton per kilogram is the same unit as meters per second squared. So this is not the correct choice as far as this question is concerned, because we are looking for a unit which is not the same as the other one. Let's look at our B. We've got Newton seconds. Again, Newton seconds. Now I'm going to adapt this one here. Kilograms meter per second squared multiplied by seconds. And I'm going to get kilograms meter. I'm going to get kilograms meters per second. And you'll be able to see that, of course, this unit is equal to this. Again, this is not the choice because this unit is exactly equal to this. In fact, this unit is the unit of impulse or change in momentum. Let's look at C. In C, we've got pascals. The pascal is the SI unit of pressure, and we have been able to see that the other SI unit of pressure is newtons per meter squared. Again, this is wrong because this unit is equal to this. Remember, we are looking for units which are not the same. So that leaves us with only part D. This must be the correct one. But I want to use this question to show that the volts per meter squared and Newton per Coulomb, they are not the same when I express each one of them into SI base units. Let's start with volts per meters squared. So first of all, I want to appreciate the fact that the volt is measurement of potential difference. Potential difference is work done divided by charge, Q. Work is force times distance. Charge is current times time. And of course, it is volts divided by area. Of course, area here is A times A. I want to work everything out completely. So volts per meter squared must be the unit of potential difference divided by area. At this point, notice that the unit of potential difference and the symbol for potential difference is the same. But of course, the symbol for area and the symbol for its unit is, of course, not the same. In physics, you will encounter such situations whereby the symbol for the unit and the symbol for the physical quantity is the same. So at this point, force, we have already seen, is measured in kilograms meter per second squared. Distance is measured in meters. Current is measured in amperes. Time is measured in seconds. Area is measured in meters squared. Of course, at this point, I'll be able to see that this meters and that meters cancels comfortably with that. And this gives me kilograms per ampere per seconds cubed raised to minus 3. So we have expressed volts per meters squared, volts per meters squared into SI base units. Let's do the same for Newton per Coulomb. Newton per Coulomb comes from force divided by charge. Force, we have seen, force is MA. Charge is current times time. The SI base units of mass is kilograms. Acceleration is meters per second squared. Divided by current, which is amperes, times seconds. And this gives us kilograms, meters per ampere per seconds cubed. So the Newton per Coulomb, this is Newton per Coulomb. Newton per Coulomb is expressed in SI base units as kilograms meter per ampere per seconds cubed. But volts per meter squared is expressed as kilograms per ampere per seconds cubed. Now you definitely can see that since the base units are not the same, it follows that volts per meter squared is not the same as Newton per Coulomb. And that is why the choice was D. So in order to compare two units, whether they are the same or not, we need to convert each one of them into SI base units. In this question, the examiner was particularly generous because the examiner provides you with a method that you can use in order to compare these units. But even where the examiner has not given you that hint that you are supposed to use SI base units to compare them, it's always important to remember that in a situation where you are required to compare two units, whether they are the same or not. So in order to compare two units, whether they are the same or not, you need to convert each one of them into SI base units.